My name is Kristoffer Strøm, and I'm the Deputy Software Lead at Vortex NTNU. I'm a third year, just finished my third year of cybernetics and robotics here in Trondheim. And as a Deputy Software Lead, I've sort of gotten to know all parts of the system, at least for the software stack, and how our sensor rig sort of relates to that. So that's what I'm going to be talking about, our sensor optimization and sort of how we've utilized our sensors to the best of their abilities. Now, as for the subsystem requirements, our number one requirement is that we have a navigation stack. We need to know where we drive, or where the drone needs to know where it is. And for that, especially now that we're running fully onboard sensors, we need sensors and a navigation stack that is resilient against drift, and that is accurate over a longer period of time. Now, knowing where you are is basically useless unless you know where you should be. And that's where the second requirement for our subsystem is, and that is object detection. We need to be able to detect objects underwater and also classify them, and in that way utilize the most out of our sensors. Now, to solve the problem of localization or navigation in and of itself, we have the DVL from Nortec, the DVL 1000, as well as an IMU that you cannot see inside the electrical housing. Those two sensors combined are very good for underwater navigation, and we utilize their performance to their absolute limits with Kalman filters, both an extended Kalman filter and an aerostate Kalman filter. Having both gives us the flexibility to switch between different ways of filtering our odometry depending on our needs. For example, the aerostate Kalman filter does not rely on figuring out tons of system parameters that would potentially take months or weeks to figure out. And if we show up to the competition not knowing those, that's really bad. Meanwhile, the extended Kalman filter, configured correctly, gives us more resiliency to drift over time, proven from our experimental results. Now, we switched out our front-facing sonar with a full 360-degree scan sonar this year. We did this because we have stereo vision, and so there's no need for depth estimation using the sonar. With a 360-degree sonar, we optimize the use of the sonar by having a full view of our surroundings. That's not necessarily detected by the camera alone. So let's say we find an object with the sonar, we can mark that location and further investigate with our camera should we want to do that. For example, if we're solving a task and we detect something else in the water with the sonar, we can save that location for the next few minutes and then go inquire further with the camera. Now, as for our confidence ratings in tasks we are able to solve, with our navigation stack, we are very confident in our ability to move through the gates and also detect and move towards static objects like the buoys, and also detect objects that we can manipulate. Now, since we do not have any hydrophones in our sensor stack, we are not very confident at all in our ability to find pingers. As for the more complex manipulation tasks, we are somewhat confident because we are very confident in our ability to actually find and position ourselves for those tasks. But since they are more convoluted and complex, we are less confident than the tasks like the buoys and the gates. Now, since we started off the fall semester with building an entirely new drone, we didn't really know what type of sensor layout we would have, nor did we have a physical model to work with. So all of our attention was focused on the simulator and solving missions using previous software, and also developing or refactoring most of our software stack, which also included a lot of the code for our previous sensors. Now, once the drone was coming together, we settled with the same IMU as our last drone and also the same DVL, which meant that our efforts previous to that semester were not lost. Now, it dawned on us pretty quickly that the simulator alone is not good enough for us to test our drone. because while it has ways to simulate odometry data, it does not have a real match between the real world and the simulator world. So around Christmas, our team scheduled pool tests at our marine cybernetics lab, and we were lucky enough to get 4 separate tests, or test days and weeks. During all of those, we extensively tested our drone, and we were finally able to test our physical system. We also had our head software lead writing his thesis on our drone, which overall left us with very good experimental results from the lab, and also gave us enough time to fully integrate the systems that we wanted. We also did not acquire our sonar until very late in our development cycle, so the integration testing part of that was also helped massively with our access to the Marine Cybernetics Laboratorium. Now, since the MC Lab also has a visual positioning system, we were able to test our localization with ground truth, or as close to ground truth as you can come. And that gave us the advantage of testing performance over time, both with the extended and the Aerostate common filters. And it also enabled us to both calibrate our cameras and test our object detection, as well as testing the SLAM that comes with our stereo vision. Now that has given us mixed results. We found that the extended common filter actually was more resilient towards drift than the Aerostate common filter. We're not entirely sure why that is the case, but we at least have the experimental data to work with. As for the sonar, we acquired that fairly late, but we were able to squeeze it in on the last pool test and get very great results with that. All in all, having the Marine Cybernetics Lab to test that proved to be a lifesaver for us, especially since we built this drone all in 1 year. Nice. Så jeg fikk med alt jeg ville si.
Fantastisk.
Bra.
Ja, da tror jeg har vi det, altså.
Yes.
Nydelig.